All right. Everybody get out worksheet 5.1. All right, begin by looking at number 1 and just label all the stereocenters, the chiral carbons, as either R or S. So kind of do that in groups, and then we'll check them here in just a second. So again, just label all of those chiral centers as either R or S. start looking at them? Let me draw this first one. All right, what are the priorities here? What is 4? Hydrogen. What is 3? CH3. What's number 1? Chlorine. And then, so that would be number 2. They didn't copy very well, but the darker lines are the wedges, and the one that's a little bit lighter is actually a dash. Okay, what did you get when you did this? All right, let's look at it. This one's actually a hard one. And I'm sorry I put this one on here. I didn't realize it until afterwards. Okay, so since 4, our hydrogen is on a straight line, you actually really need to look at it in 3-dimensional space. Usually what we do will still work, but anytime it's on a plane, you'll want to check it. So if I have, let me get a model here. Let's say the top one, the white one there, is our 4. That would make chlorine here, right? Number 1. So yeah, 2 would be OH. Okay, so let's look at what happens with these 2 here. Okay, so is number 4 going back or away from you? No. So let me flip it over there. Okay, now it's going back, right? All right, now let's look at this. This would be, this was the chlorine, and I don't remember the rest of them were. Is OH the blue? Okay, so it's chlorine, OH, CH3. So 1, 2, 3, right? So what do we get? R. Right? 1, 2, 3. You probably did it. So this one I think actually worked out. Let me see. 1, 2, 3. It looks, what does it look like? It looks counterclockwise. And then is 4 on a dash? No, so it changes. So that one worked out just fine. It did follow a shortcut. All right, let's look at the next one. Okay, so going left and right, is that a wedge or a dash? Wedge, so let me just draw those in, and then up and down, dash. Okay, so that's one thing to remember. Now let's do priorities. What is number 1? OH. What's 4? H. And then between these 2, which one would be number 2? Top one. Because this is a CH2 with an OH, and this is just a CH3. CH3 is usually a really low priority. Okay, are we going to change what we see? Yes. Why? H is on a wedge, it's not on a dash. So it looks like 1, 2, 3. It looks like what? Yeah, it looks like the S, so it's R. Okay, so let's look at this one. This carbon here, it shows wedges and dashes. Is it a chiral center? No. Why? There's not 4 different groups coming up there. Do you see there's 3 hydrogens? Okay, you have to have 4 different things coming off of there. So let's look at the next one. Is that a stereocenter? Yes. So let's look at why. You say I have hydrogen, OH. This carbon has a chlorine bromine, right? And this carbon is just a CH3. Okay? So that one is a chiral center. So now let's label our priorities. So what's number 4? The H right here. What would be number 1? OH. Now I have CH3 or carbon with chlorine bromine. The chlorine bromine. Then methyl. Do we need to change what we see? No. So we see 1, 2, 3, which is what? S. Now let me redraw that. I'm just going to put CH3 right there. Okay, so now let's look at this last one. Is this a chiral carbon? Yeah, let's look at our groups. We have, you see, hydrogen, chlorine, bromine, and then this large carbon group there. So you see 1, 2, 3, 4. Do any of them look the same? No. So now let's label our priorities. What would be 4? H. What is 1? What? Bromine. 2, chlorine. And 3, carbon group, right? Do we need to change what we see? No, because our number 4 is already on the dash. So let's see what we see. There's 1, 2, 3, which is S. If it helps to circle the different groups, do that. All right, let's look at the second one here. All right, let's look at this one first. So let me draw the original. I want to draw the enantiomer of this. How would I do that? Keep the top and the bottom the same. Yeah, and flip the H and the OH. So I'm going to reflect the OH, and then on the other side I'll put the H. So you pretty much just switch everything going left and right. So hydrogen here is pointing left, right? And hydrogen here is right. So you're switching the direction those are pointing. All right, so here's the last one. How would I make this into an enantiomer? What am I switching here? So here I switch left and right. Okay, and then what do I switch down here? Wedge and dash. So I draw everything the same. Okay, so I'll give you a second to draw that. Okay. So do you see I have CH3 coming up there, bromine, and the dash and the wedges are in the same position. But down here, what am I going to put on this dash? OH. And on this side, H. And then what about out here? Cl. Then right here, H. So I'm just switching. You see what's actually on the wedge and the dash. All right, what is an enantiomer by definition? Mirror image. Can they be superimposed? No, so they're non-superimposable mirror images. What about their physical properties? The same, all the same. Do they rotate light differently? Yeah, they can rotate the direction of light. Does that rotation necessarily have to do with R and S, the direction? No. So remember, an R enantiomer could rotate light, clockwise or counterclockwise. That's always experimentally done. What about a diastereomer? What is a diastereomer? Yeah, pretty much not an enantiomer. So an enantiomer, remember, we switch the stereochemistry. So if we have RS, then the enantiomer is SR. Okay, so they change. So if I write that down, if we found RS, the complete opposite of that, which is the enantiomer, would be SR, right? Okay, but for a diastereomer, cover of this one, I might have SS or something, right? Did this one switch? RS? Yeah, but did SS switch? No, so basically, if not all of them switch, then it's a diastereomer. And it depends. Sometimes all but one switch. Sometimes only one switches. It really depends. Basically, if not all of them are complete opposite of what it should be, your stereocenters, then it's a diastereomer. And then what about identical? Be the same, right? So if I had RS, then the compound, the stereocenters would also be RS. And what about the physical properties for a diastereomer? Are they the same or different? They're different. Right, so let's finish up this chapter. There's only a few slides left. Don't worry about alkenes, tumor centers. Okay, so basically what this slide tells you is if you have two molecules, okay, and assume they have a chiral center, then the three choices you have, either the relationship is that they're enantiomers, which means they're complete opposites of each other, they're diastereomers, which are not complete opposites of each other, or identical, which means they're the same thing, okay? So those are sort of your three choices. So I could give you, two compounds and ask, are these enantiomers, diastereomers, or identical, okay? Sometimes it's easy to see, sometimes it's not. When in doubt, if you label them R or S and just compare that way, that's sort of, assuming you can do R and S, correct? That's a good way of checking yourself. The other thing that comes up is what's called meso. Okay, these have an internal mirror plane. So let me show you what that looks like. Here, for those who like flowcharts, let me show you this. These might help. So what you can look at comparing structures, are the structures connected the same, or different? So are they connected the same? Yes, like the same, if chlorine's coming off the same carbon, bromine. If they're not connected the same, remember those are constitutional isomers, okay, where they have completely different connectivity, different branches, everything, okay? If they are connected to the same, then it's some sort of like conformer, okay? Then you look, are they mirror images of each other? Okay, like complete opposites. Yes, they're enantiomers. No, then they're diastereomers, okay? Is there a plane with symmetry? Yes. Okay. So let's look at this. Let me show you what meso looks like. Right here. Okay, so do you see right down the middle right here, this is where we're looking at the plane of symmetry. These molecules reflect each other, like within the molecule. So do you see here? CH3 on top, CH3 on bottom. Bromine in the middle, bromine in the middle, HH. So if I folded this in half on top of each other, so I can fold CH3 on top of CH3, right? Bromine on top of bromine, hydrogen on top of hydrogen. So there's that plane of symmetry. You see the same thing right here. Those are called meso compounds. So a compound can be meso and a diastereomer. Okay, so meso is something within that molecule. It's not a relationship. Okay, you're not actually comparing two. Okay, you are looking within the molecule. So enantiomers, for example, let's look here. Do you see here? These are labeled as 2R, 3R. So then the enantiomer would be 2S, 3S, right? And that's what you see here. And then from here to here, there's a diastereomer. So we have 2S, 3S, and they said the diastereomer is RS. So you see S switched to R, so that one reflected, but S stayed at S. So that's the diastereomer, okay? But do you see, comparing these two here, this one is meso, but is this one meso? Can I fold it on top of itself? No. So that's a completely different question. So I could ask, are these enantiomers, diastereomers, or identical? And then I can ask, are any of these compounds meso? Okay? So meso is not a relationship. It's something you see within a compound. Okay? The other thing is that an enantiomer of a meso, so the reflection, do you see that the CH3 stay the same, and do you see H reflects H, H reflects H right here? So it looks like an enantiomer, right? And if you look here, RS, SR, okay? So they switch. R switch to S switch to R, okay? But what you find is that it's actually the same compound, okay? So let me see if I can make this for you, maybe. One. Because it's hard to explain that without doing with models. So it is the opposite, but you can actually rotate it to become the other one. So our single bonds, are they constantly rotating? Yeah, they can rotate. Can double bonds rotate? No. Single bonds can rotate, so they will. Just entropy, they like to rotate. That's the whole point of doing like the Newman projections, to show like the energy involved in rotating. But pretty much all single bonds will rotate. Okay. Hold on. Almost there. Okay, here they are. Wait. Here we go. Okay. No, you can't see that. There we are. Can you see that these are reflections of each other? I have the white ones here. So these will be the same. But like the reflection here, so I have green and green reflecting each other, and then the purple's on this side. So the purple is on which side here? Left, but on this side it's on the right. So remember, when we switch these, you just switch left and right, okay? Now, in an enantiomer, it's the opposite. It's a mirror image, so this does look like the mirror image, and it is, okay? But it also has to be non-superimposable, right? So I should not be able to stack these on top of each other anyway at all, by definition, Okay? So let's see here. Let's do, the whites are pointing up, so let me just stack this way. Stacking this way, does purple match with purple? No, not right now, but what if I do this? Did I do anything? Did I break a bond to rotate it like that? No. So now let me see. The whites are still going up. Do the whites match? Do the purples match? Do the greens match? Yes. So these are the same exact compound. All I did was this, to turn it into that one. So, and do you see that it's meso? Do you see the reflection right here? Do you see purple reflects purple? Green reflects green. White reflects white. So this has a plane of symmetry right here, okay? But its reflection, its mirror image, is actually the same compound. And that will always happen. In the Chapter 5 notes, I try to write it like 5 times on there and underline it and circle it, okay? So anytime you have a meso compound, you'll see that it's meso. And if you're comparing, so you see that that's meso. If you look, and if something looks like the enantiomer of a meso, it's actually the same. So an enantiomer of a meso compound is actually the same compound. So an enantiomer of a meso compound. So the original is meso. You take the mirror image of that equals identical. No, it's not even called an enantiomer. It's actually just identical, same compound. And let me show you. So let's make these not meso. So if I move this, let's switch these two here. So switch. Wait. Yeah. Okay. So are these meso? Let's just look at this one here. Do they reflect each other, the colors, top and bottom? No, I can't fold these on top of each other. And is this the mirror image of it? Purple, purple match up, green, green match up. So it's going to be a mirror image. Okay? So by definition, this isn't an enantiomer, but let's make sure, and none of these are meso. So let's prove that we cannot stack these on each other, no matter what. Okay? So I move this here. The whites and the whites match up to the purples and the greens. No, so let me rotate it this way. Do they match up here? No matter what I do and how I rotate it, it doesn't matter. They'll never match up. So do you see that? So these are different. These are enantiomers, okay? Versus the other way, when basically you're going to find they're both meso. If they're both meso, that means they're identical, okay? Anyway, so that's why it's hard to show you. I think it looks better with the models than to see it here, because these almost look like I can rotate it into this, and these obviously can. So anyway, just remember the models, that enantiomers, by definition, cannot rotate on each other. They cannot stack on top of each other. Meso enantiomers can. Those are identical. Properties of diastereomers, we already talked about this. They have completely different physical properties. Melting point, boiling point, everything's different. So these are easy to separate in the lab, versus enantiomers are not. Okay, so let me show you this. This is kind of a neat way. So enantiomers, can we separate enantiomers in the lab if we leave them as enantiomers? By physical properties. No, they're the same. Okay? So let's look at this. I have R and S 2-butanol. So I have my R, I have my S. Those are my two enantiomers. Okay? Now I can do a reaction. Okay? And I'm going to react it with another chiral carbon. Okay? This chiral carbon is called RR. All right? Now, when I react, let's say R with RR, I combine them, what do I get? RRR, right? This is all I'm looking at. We're combining them. So if R combines with the RR, I get RRR. So then what do we get with this one? If we combine it then with the S? SRR. So when I react these here, when the R reacts with it, I get RRR. When the S reacts with it, I get SRR. Okay? Do you follow that so far? Okay. So now let's look at what these are now. So my R changed to an S. Did that reflect? Yeah. R is R. Did that reflect? No. R to R. Did that reflect? No. So what are these? Diastereomers. Now can I separate them? Yes. And so that's one thing they'll do in the lab is if you react enantiomers with a chiral center, you'll create diastereomers. Okay? And then from there, it's pretty easy to separate these two here. But anyway, so it's kind of a little trick thing that they do there. And then also, another one is with this resolution. So this is chromatography. We did it with the paper. Do you remember the different ink, or you did inks, you did dyes? They should smear at different lengths and different colors. Anyway, you could see the different components and everything, right, of the dyes. Well, and why are they coming up at different points? Why is, a blue lower than a red or whatever you saw? Why do they have different height? Yeah, so different intermolecular forces. So, different attractions to the solvent, really. Okay? So what you do here, instead of using paper, they use usually like a silica gel kind of thing. And then they put this solvent in there. So this is going to react just like paper. So just pretend this is paper right here if you want. Okay? And this paper, though, is chiral. Okay, remember, chiral compounds can tell the difference between other chiral compounds, always. Okay? So if I do that, they're going to have different attractions to the paper. Think about with our nose. Okay, remember I told you the caraway seeds, which is the pizza Italian seasoning, versus spearmint. Can we smell the difference? Why? The receptors in our nose are chiral. Okay? So a chiral compound can tell the difference between another chiral compound. All right? So if this quote-unquote paper is chiral, can it tell the difference between the enantiomers? Yes. And so do you see these little colors right here? One's blue, one's whatever that is. Okay? Reddish, sort of. Do you see that they're coming in at different heights? Because they're separating them because now they're attracted to this column to different extents. Anyway, so they'll come down, they'll drop down at different times. Anyway, so it's just another way. So either you can react an enantiomer with another chiral compound and separate them that way, or you could put them in a column, and in the column you're going to have another chiral compound and separate them. So basically the moral of the story is chiral compounds can tell the difference between other chiral compounds and can be used to separate them. All right, so that's pretty much all the slides, but let me look at, there's a concept you'll need to know. And if we look at worksheet 5.2, let's look at number 2 is a really good one. Okay, let me draw this first one here. Okay, looking at these here, the relationship here. I want to know, are these identical enantiomers or diastereomers? Identical. Why? Yeah, they're meso. Do you see going across here? Both of these, CH3 reflects CH3, H to H, OH to OH, OH to OH, H to H, CH3 to CH3. So what do we call that when there's a reflection? Meso. So this one is meso. That one is meso. Do these look like reflections of each other? Yes, you see OH reflects there, OH reflects there. So they appear as enantiomers, but we remember that two meso compounds that appear as enantiomers are actually identical. Okay, now let's look at the next one. You can start looking at it while I'm drawing this. So look at those. Try to decide what that one is, and then I'll draw the next one while we're at it. Okay, let's look at the top one. Are any of these compounds meso? No. Why? The top and the bottom. The middle looks like it's meso, right? But whenever you actually compare it's on the top and the bottom. Do you see they're different? So they're not meso, okay? So we don't have to worry about that identical trick there. Okay, so then are these actually reflections of each other? Yes. I'd always just compare right here, really. Do you see that they're the same? And that pretty much means it's going to be a reflection. So what do we call that? Enantiomers. Oops. Okay. What about the bottom one here? Are they reflections? Are they meso? So what do we call that? Enantiomers again. Diastereomer. Let's draw one. So if the original looked like this, let's just say, what would a diastereomer? Let's draw the diastereomer. Okay, so just like you would with an enantiomer, you leave what's going up and down the same. Now, if it wasn't an enantiomer, what would I do? You reflect everything, right? So that you'd have your OHs both on this side. But it's not an enantiomer, so what do? I only do that for one of them. So let's say I'm going to reflect the first one, and then the last one will do what? Stay the same. Still have H, OH. So you see these two reflect right here. You see they look like each other. But do these two reflect? No, OH and H aren't the same. So that's what a diastereomer would look like. So one would reflect, and at least one would not. The other thing we want to look at is converting these into Newman projections. Okay, so let me show you. Okay, so this one's kind of similar to that one. So let's look at, let me move it over. This one, okay? So let's say our CH3s are the white ones. So let me put, these are white. Then that would make our OH green, and then our H purple. Okay, and if I flatten this kind of like that, can you see that that looks just like the Fisher projection, right? Okay, now let the Newman projection looks like that, right? Remember we did the Newman projection? So that's the difference. So it's either you're looking at it like flat like this, okay, or up like that. So it's just here to here. That's all it is. So let's draw this. So did I change anything? So do you see I have my white, my two whites going up and down, right? And then green, purple, purple, green. Okay? Now when I do this, when I flip it into the Newman, what kind of confirmation is that? Is that staggered or eclipse? Eclipse, yeah. And so actually every time you draw it like this, you're actually doing the least stable Newman projection. Okay, so let's draw this. So I have a circle, or I mean a dot and a circle. What's coming off my dot there? This is the white one, which is what? CH3. And then the green one, let's see over here, is OH, right? And then purple is hydrogen. So do we agree if I put that on top of it? CH3 on the front one, OH, H. Now let's do the back one. What's going straight up? CH3. What's to the bottom left? H. And then what's over here? OH. And then from there, you can rotate them into the various staggered eclipse conformations. But I just wanted to show you how you go back and forth between the two. And it's pretty simple. So these here, so do you see this always converts into the least stable right here? Okay, yeah, this is the like a total kind of eclipse here. So I have CH3 with CH3. And these here going up and down, these are always your top right here. Okay, going up and down is your top. Now, what direction is OH pointing? Like left or right? Left and H? Right. So do you see over here I have my left and my right? Or my, or left, sorry. And then over here I have right, H, OH on your right. So these, if it's pointing to the left, it's going to be to the left. If it's pointing to the right, it's going to be to the right. And these are always going down, right? Do you see that these are pointing down? They're always pointing down when you're converting back and forth. So this is always down left, down right. And these are always pointing up. Now, which one's your front and back carbon actually doesn't matter. We drew it as that is my front, that is my back, but you can do it that that's your front, that's your back. That doesn't matter. I mean, it's like saying, if I go like this versus this, did I change that compound? No, so that doesn't matter. But just know that these are, whichever one you decide is your front, this one or that one, these are always going up. These are left down, right down, okay? That's about it. So they're actually pretty simple to do. Anyway, I just wanted to show you that the difference between, here to here. So, anyway, they're very similar. This is just how you're looking at it. All right, so let's take a break. All right, what we're going to do for about 20 minutes, we're going to introduce Chapter 6. And then the last 30 minutes, I'll pass out the exams. And then I already have the exams paired up. Okay? And what you're going to do is basically go over the exam together with your partner. Okay? You can borrow some scrap paper or whatever. The exam grades are already recorded. Okay? So you can't, erase your answer and tell me you got something different. Okay? Now, if you do have a question about your grade, feel free to, come and ask me. But I'm hoping with the pairs, you'll be able to work out together what you missed, okay, and understand that. So we'll go over that the last 30 minutes. So we'll say at 3:20-ish, we'll stop this. All right, so Chapter 6. This is sort of the beginning of organic chemistry synthesis and reactions. Okay? And what we're going to be looking at is substitution and elimination. So now that we've done all of the radical reactions and we did those mechanisms, now you're going to find that nothing else is like those. Okay? So kind of temporarily put those out of your mind. The rest of organic chemistry will be like this. Okay, so we're going to be looking at alkyl halides. An alkyl group is an alkane, okay, just a carbon chain. And a halide, what's a halide? Halogen. So it's a carbon chain with a halogen. Okay, so we're going to be looking at alkyl halides. Alkanes with halogens is all that means. And you can look, there's vinyl and aryl ones, but the big one we're going to be looking at is alkyl halide. Okay? Are halogens polar? Are they very electronegative? Yes. So if we're looking at a carbon bonded to a chlorine, which one would be the most electronegative, carbon or chlorine? Chlorine. So that would have your partial negative, and so your carbon will be a partial positive. Now, because your carbon's partial positive, it makes this carbon reactive. Okay, it wants more negativity, if you want, towards it. So that's what causes the reaction. So anytime you have a carbon bonded to an electronegative atom, it's going to usually cause some reaction. Okay. Now, looking at naming these a little bit. It's the same exact rules we've been using. And how you name these, chlorine as a branch, so these are always branches, is called chloro. Bromine as a branch is called bromo. Fluorine as a branch is called fluoro. And iodine as a branch is iodo. Are they listed anywhere on there? Probably not. So it's chloro, fluoro, bromo, iodo. So if we look at this one here, how many carbons in the longest chain? 4. 1, 2, 3, 4. What do we call 4? Butane. Now, what's our branch? Chloro. And what carbon is that on? 2, because you find the end is closest to, which is right here. It's 1, 2. So this is 2-chlorobutane. And you see that's correct. Ignore this next one because they get into things I don't want to go into right now. But let's look at this one. What is the longest chain here? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, 9. What are our 2 branches? Methyl and bromo. And what carbon is the methyl on? And this is on 6. Which one comes first in the name? Bromo. So I'm going to have 6 bromo, 2 methyl, no name. Right? So let's check. 6 bromo, 2 methyl, no name. And why does bromo come first? Alphabetical order. It has nothing to do with the numbers. The numbers just tell you what carbons they're on. Okay? It has to do with alphabetical order. Let's look at here. What is this called? Cyclohexane. Okay? And this is called bromo, and that's called fluoro. Which one would come first in the name? So we have bromofluorocyclohexane. Now we need to number it. How do we decide that? Which one comes first? Bromine. Why bromine? Alphabetical. Because we look, do they have the same amount of branches? You see, this one has, we ignore the hydrogens. Hydrogens are never branches. This has one branch, right? So that help us? No. So then we're looking at a bromine versus a fluorine. Bromine comes first alphabetically, so it's numbered first. So it's 1, 3. So if we look at the whole name, we forgot the part. So here, how are they? Are these a cis or a trans? Cis, yes. Now, anytime you show the wedges and dashes on a cyclic structure, you will say that it's either cis or trans. What if I had wedges and dashes on this structure? Do I say cis or trans? No, single bonds do not have cis-trans. What can be named as cis and trans? Double bonds and cyclic rings. Okay, those are the only two. So I don't want you to get confused in it, because if this showed wedges and dashes, don't put like cis methyl trans. I don't know. So single bonds, even if it shows wedges and dashes, you see it's just a straight chain, single bonds, no cis or trans, no matter if it shows a wedge or a dash. But cyclics and double bonds can be cis-trans. So here we have cis, 1 bromo, 3 fluoro, cyclohexane. So everything's the same. It's just now we introduce a new branch. It's either chloro, bromo, fluoro, or iodo. Don't worry about the common names. Some of these you might have heard of, though. The common name. So there's like, have you heard of chloroform? Okay. That is a carbon with 3 chlorines. Okay, so anytime you had like the halo form, so like bromoform, iodoform, or in this case chloroform, form means 3 of them. See, there's methylene chloride. You might have heard of that one. Those will end in, those are at 2 of them. Carbon tetrachloride. Tetra meaning how many? 4. And that's about it. Anyway, so those are ones you might have heard of. So those are common names. I'm not going to have you memorize common names. But those, just in case you see them somewhere, those do not follow the IUPAC name. Those are just names, like a nickname, if you want. Okay. Classifications. So remember with carbons we did primary, secondary, tertiary. So a primary carbon was attached to how many carbons? 1. A secondary, 2, and tertiary, 3. And we can label these the same way. Basically find where your halogen is, so right here, connected to that carbon, and then label that carbon as either primary, secondary, tertiary. So what would that, I'm only looking at carbons it's bonded to. So how many carbons is it directly bonded to? 1. So this is called a primary alkyl halide. Or alkyl just means carbon groups with a halogen. So this one's a primary. What about this one right here? Tertiary. So it's connected right here. And on this carbon, there's directly bonded 1, 2, 3 other carbons. So it's a tertiary. And in this one here, secondary. So it's bonded to 1, 2 carbons. So look where the halogen is, with the carbon it's attached to. Whatever you would classify that carbon, that halogen's classified the same. types of dihalides. So di meaning how many? 2. Halides, halogens. So different types. There's geminal, which means they're on the same carbon. And vicinal means they're on neighboring carbons. So do you see here the bromines are on the same carbon? They're bonded to the same one, so that's a geminal dihalide. And do you see here these are on neighboring carbons? So that's the vicinal. Uses of alkyl halides, anesthetics, Freon in your refrigerator, that is a alkyl halide. Pesticides, they don't really use this anymore, but that is a alkyl halide. Like DDT. The only time they ever use pesticides with alkyl halides is if maybe you're in Africa or something and there's like this huge outbreak of malaria, so it's kind of like, you know, using DDT or having malaria. So it has to be like extreme cases that they actually use it. They don't use it over here really anymore. Freon and everything, a lot of your alkyl halides, actually they don't use a lot anymore unless it's kind of what we're doing, basically react it to make it into something else. A lot of these, you see here like Freon, was really harmful to the ozone layer. So the ozone, do you know what ozone is chemically? O3. Okay, it's just kind of like oxygen is O2. This is just 3 oxygens bonded together. Well, it's very reactive to other halogens. Okay, so what happened was the halogen was reacting with the ozone, and whenever 2 things react, it makes something else, right? Something new. So what happened was, like Freon, for example, was converting ozone into a completely new compound, so it was depleting the ozone that was in the atmosphere. So anyway, that's what happened. So it wasn't a hard fix. Basically, they realized not to really use Freon and stuff anymore. But that's why, because it was actually reacting with the ozone. You know, they talked about the ozone hole, right, the layer. Anyway, that was what that was. Okay, dipole moment. Basically this, all you need to get from this is when carbon's connected to an electronegative atom, like a halogen, it makes that carbon reactive, okay? Because it gives it this partial positive sign there. Now, if it was just connected to hydrogens, are those polar or nonpolar? Nonpolar. So there's no reactivity there. But whenever I bond carbon to a very polar atom, you know, something that's electronegative, then it creates a reaction there. And again, we'll look at that. Boiling points. So if we're going to look at the intermolecular forces, do alkyl halides have dispersion forces? Yes, everything has dispersion forces. What about dipole interactions? Yes, it has a halogen. Is halogen electronegative? Yes, so it has the dipole interactions. What about hydrogen bonding? No, because the halogen, well, I guess if you look at fluorine. But okay, forget fluorine for a minute. Do the others hydrogen bond at all? No. So these pretty much follow the same trends. You know, the greater the mass, the higher the boiling point. They're all going to have dipole and dispersion forces. So basically, the larger and the less branching, you have more out, the higher the boiling point. Densities with these, all you need to look at. So what are your 2 lightest halogens? Fluorine and chlorine. Those are your lightest ones. So basically, those are less dense because density is mass over volume. So if your mass is less, your density is less. And then your bromines and iodines, those weigh more, and so the density is more than water. And then this was just saying dichlorides because you got another chlorine. But anyway, so basically, with all density, the more you weigh, the more dense you are. preparations, we've already done these, so I'm going to actually skip over this section. But how you prepare alkyl halides is you do a radical reaction. Okay? Do you remember when we would have like this and react it with Cl2? What all did we create here? Which acid did we make? HCl. And then what did we put on this carbon group? A chlorine. So do you see that we made a alkyl halide? Okay, so all your radical reactions we did, one of the products was always an alkyl halide. So they just kind of like summarize radical reactions again. The last slide I do want to show you, though, you can skip over all that. It's just the summary of basically the main point of this. So what we did before, sort of an introduction, what is an alkyl halide, how do you name it, and then look at like boiling point, intermolecular forces. What we will do in this chapter, starting on Monday, we're going to look at SN2, SN1, E2, E1 reactions. Okay? So the S's, do you see here? Those stand for substitution. So do you see there's two types of substitution? And then E stands for elimination. So we see two types of elimination. So just to clarify what substitution and elimination are in terms of chemistry, let's look here. Do you see this is called a nucleophile? So you have a base and a nucleophile. What does a base do? What does it take off? Hydrogen. So the only role of a base is to take off a hydrogen. A nucleophile is usually the same compound as a base, except its role is to make a bond to an electrophile. Okay, so you have a nucleophile and an electrophile. Now for organic chemistry, the electrophile is pretty much always carbon. Okay, so for our class, the nucleophile always wants to make a bond to carbon. The electrophile is basically your atom that has the partial positive. So if we look here, do you see carbon? X stands for any halogen. So let's say there's a chlorine on there. So if that was a carbon-chlorine bond, where would our partial positive be? On this carbon right here. So that means it's an electrophile, if you have a partial positive. And nucleophile, what sign do you see here? Negative. So this has a partial positive, this has a negative. Do you think they're attracted to each other? Yes. So what happens if we look at substitution, the nucleophile is actually, because substitution, what does substitution mean? Like switch, okay? So you see overall, the nucleophile is going to take the place of the halogen. So you see the nucleophile is here, and then the product, it's where the halogen was. And then the halogen's over where the nucleophile is. So they will switch places, okay? And we'll go over more in depth what that looks like and everything. But at this point, know that a nucleophile wants to make a bond to a partial positive carbon, which is called an electrophile. And for a substitution, nucleophile and halogen switch. Now, if we had elimination, what does elimination mean? Get rid of, right? So if we see here, in the end, so do you see there's an H and an X right here? And in the end, are those H and X on there? No, so we completely eliminated. Did we substitute anything in their place? No, I mean we have a double bond there, but is there any other atom substituting there? No, so there wasn't a substitution. We just got rid of two of them. And notice, what do I make over here? What's a double bond? An elimination will always end up making a double bond. And what do I have right here? This is a base. And again, what does a base do? It takes off a hydrogen. So do you see over here, what is it bonded to? The hydrogen in the product. Anyway, so we'll look at how that occurs, okay? But the substitution switches, and the elimination eliminates and makes a double bond, okay? And we'll go more in depth, way more in depth than probably you ever wanted to go, starting on Monday. But right now, just kind of understand the definition. What's the difference between a substitution and elimination? All right, so now let's go look at your exams. So I'm going to pass them out. So I'll just say your name, I guess, and then just come up here. I'm going to go by last name. So Biddick. Thank you. You are going to be partner with Romanes. Is that how you say your name? Is that correct? Okay. If I say your last name wrong, sorry. Here you go. And you're going to be partnered with her.